California, a neighborhood sitting right next to the Port of Los Angeles, Wilmington. At some point, the ground here dropped by about 30 feet, roughly the height of a three-story building. This wasn't a sudden event like an earthquake. It unfolded over decades, slowly but unmistakably. Here's the strange part. There was no giant underground cavern that collapsed. The ground wasn't hollow, and yet the city kept sinking anyway. What triggered all of this was the oil being pumped out from directly beneath people's feet. Most of us picture it the same way. Pump out all the oil, and you're left with one massive empty cave underground. Turns out, that image was wrong from the start. In today's video, we're digging into exactly what happens underground once the oil is gone. We'll correct some geological myths most of us take for granted, and follow the story all the way to how humans actually managed to stop a sinking city dead in its tracks. If deep dives like this into geopolitics and science are your thing, go ahead and hit subscribe and drop a like. Let's get into it. First, let's get a real sense of just how much oil we're pulling out of the ground every single day. 1 barrel of oil is about 42 gallons, roughly enough to fill up a standard bathtub. And right now, as you're watching this, humanity is pulling about 100 million barrels of oil out of the ground every single day. Convert that to volume, and you get about 4.2 billion gallons a day. That's the equivalent of draining roughly 6,000 Olympic-sized swimming pools completely empty every single day. 6,000 pools yesterday, 6,000 today, 6,000 tomorrow. And since the start of industrialization, humanity is estimated to have pumped out over 1 trillion barrels of oil total. So here's the obvious question. If we're pulling out that much material every single day, does it really leave the ground underneath completely unaffected? Spoiler, no, it doesn't. And the result showed up in the most destructive way possible: an entire city sinking into the ground. Let's go back to the Wilmington oil field. This isn't some story from halfway around the world. It happened right here, in California, in the United States. Serious oil drilling started here back in the 1940s, but over time, something strange began to happen. The ground started sinking, little by little. Records show that in a single year, the ground dropped by more than 2 feet. By the end, this area had sunk close to 30 feet total, the exact height of a 3-story building. That's the equivalent of an entire building vanishing straight down into the earth. The problem is, this wasn't some empty field out in the middle of nowhere. This was a working port city full of people and businesses. The harbor docks slowly started flooding as the water crept up, and railroad tracks that used to run perfectly straight ended up warped and twisted. The city's infrastructure was quietly but unmistakably being swallowed into the ground. And Wilmington isn't a one-off. On the other side of the world, the same thing has been happening around Venezuela's massive lake Maracaibo. Oil fields around the lake have been pumping since 1914, and over that long stretch of time, the ground here has sunk by a total of about 16 feet. The worst part is that this area sits right on the edge of a huge lake. The moment the ground level drops below the surface of the lake, the whole town is at risk of going underwater. So the people living there have built massive levees just to hold the lake back and keep it from swallowing the town. And the more the ground sinks, the higher and longer those levees have to get. It's a fight with no real end in sight. So this is where draining 6,000 Olympic pools worth of material out of the ground every day gets you. A city in California sinking 3 stories down, and a city in Venezuela holding the line against a flood with an endless wall. At this point, you're probably picturing the same thing everyone else does. All the oil gets pumped out, leaving behind one giant hollow void, and then the ceiling of that void collapses, taking the city down with it. It's basically a scene straight out of a Hollywood disaster movie. But scientifically speaking, that giant cave doesn't exist anywhere underground. So the question is, if there was no giant void collapsing, why did a perfectly fine city slowly sink into the ground? To answer that, we first need to completely reset how we picture an underground oil reservoir. A lot of people imagine a huge underground lake of black crude oil just sloshing around down there, probably because of every movie scene where oil goes shooting up like a geyser the second a drill bit hits it. But the real geology is completely different. Oil isn't pooled somewhere as a standalone puddle, it's soaked into microscopic pores inside solid rock. Think of it like a sponge soaked with water. From the outside, it still looks solid, but inside, it's packed full of liquid until you squeeze it hard enough. Underground oil reservoirs work exactly like that. On the outside, it looks like solid rock, but inside, it's basically a wet rock sponge with crude oil filling countless microscopic pores. Now imagine sticking a straw into that soaked sponge and sucking the liquid out. That's essentially what drilling does at a real oil field. So once the liquid is gone, is the rock left completely hollow inside? No, and this is the key to understanding what's really going on. Those microscopic pores in the rock sponge were never just empty space to begin with. The oil and water filling them were actually acting as load-bearing support for the entire rock layer above. The reason those pores didn't collapse under thousands of feet of heavy rock pressing down from above is that the fluid inside was holding that pressure up. In geology, this is called pore pressure, basically the internal pressure that lets those microscopic pores resist the weight bearing down on them. So what happens when you pump that oil out? The resistance holding those pores up disappears fast. It's the same idea as air slowly leaking out of a fully inflated balloon. The moment that support vanishes, the massive weight of the rock above comes crashing down and crushes those pores flat. It's exactly like squeezing a water-soaked sponge in your hand until it goes flat. Now, stack that microscopic compression across a rock layer thousands of feet thick, and the whole layer gets thinner, and everything sitting on top of it, the ground surface and the entire city's infrastructure, sinks right along with it. So it's not that a cave collapsed underground, it's that the rock sponge itself got compressed and thinner, and that's what caused the ground to sink. What's worse, once that pore structure gets crushed, pumping water or oil back in later doesn't easily undo the damage. It's like stepping on a paper cup. Even after you lift your foot, it never pops back to its original shape. Once underground pressure drops to a level the rock has never experienced in its entire geological history, the resulting sinking becomes a nearly permanent, irreversible scar.
By now, this should feel like a completely different problem than the one you started with. We were all picturing the collapse of some massive, hollow cave, but the real culprit was the shrinking of pores too small to even see. And if you think oil is the only thing coming up out of the ground during drilling, that's only half the story. What's actually inside those huge tanks pulled up from underground? We naturally assume it's all black crude, but in reality, there's another liquid that makes up a much bigger share than the oil itself. It's extremely salty brine. This high salinity liquid trapped alongside the crude oil deep underground is called produced water in the industry. It's the salty wastewater that comes up as a byproduct of drilling. The problem is the sheer scale of this wastewater. Globally, pumping 1 barrel of oil produces on average about 3 barrels of wastewater. At oil fields here in the US, that ratio climbs above 5 barrels of wastewater per barrel of oil. And at older, more depleted fields, it can hit as much as 10 barrels of wastewater for every single barrel of crude. So the vast majority of what those massive drilling rigs pull up around the clock isn't the oil we actually need. It's wastewater loaded with salt and contaminants. Inside U.S. borders alone, produced water is estimated to reach somewhere between 60 and 70 million barrels a day. That's how much high salinity wastewater comes pouring up to the surface every single day. So how do energy companies deal with all this wastewater? They can't just dump it into rivers, and dumping it into the ocean is illegal too. So the industry's go-to solution has been to force this massive volume of wastewater right back underground. Using ultra-high-pressure pumps, they inject it back into the same depleted reservoirs the oil came from, or even deeper rock layers. But this method doesn't wrap up as cleanly as it sounds. Environmental researchers have repeatedly warned that this deeply injected, high-pressure wastewater can seep into shallower drinking water aquifers and contaminate them. And here's the part that really catches people off guard. This wastewater disposal process itself is literally starting to shake the ground. Let's fact-check an old rumor while we're at it. You've probably heard some version of this. Underground oil acts like grease between tectonic plates, so once you pump it all out, friction increases and you get earthquakes. Sounds plausible, but there's zero geological basis for it. In fact, physics says the opposite would happen. If you actually removed the grease from a fault, friction would go up and the rock would lock together tighter, which should mean fewer earthquakes, not more. On top of that, the thing that actually lubricates a fault is water, not viscous crude oil. So the whole idea that pumping oil itself causes earthquakes is wrong from the very premise. But here's where it actually gets shocking. There is a clear causal link between the oil industry and earthquakes. It's just that the mechanism is nothing like we assumed. The real trigger for these earthquakes isn't extraction, pulling resources out, it's injection, pushing wastewater back in at high pressure. When you force tens of millions of barrels of that high salinity wastewater deep underground with ultra-high pressure pumps, that pressure travels all the way to old, dormant fault lines, and once it gets there, it slowly starts to break down the balance of a fault that's been locked tight by friction for ages. Picture two thick books pressed tightly together and a single drop of oil seeping in between them. Once that reaches a tipping point, the books suddenly slip. That instant when a fault can't hold the built-up pressure anymore and suddenly slips, that's exactly what shows up on the surface as an earthquake. The place that proved this beyond doubt through real disasters is Oklahoma. From 1978 to 2008, Oklahoma averaged about 2 earthquakes of magnitude 3.0 or higher per year, practically silent. But by 2015, once underground wastewater injection had exploded in volume, that same state was seeing about 900 earthquakes of that magnitude in a single year. That's a 450-fold jump from the historical average. It didn't take long for a geologically quiet state to turn into an active earthquake zone. In 2011, Prague, Oklahoma, was hit by a magnitude 5.7, and in 2016, Pawnee, Oklahoma, saw a magnitude 5.8, one strong quake after another. Here's another thing worth pointing out. The main driver behind this earthquake surge wasn't fracking, the rock fracturing extraction method environmental activists usually point the finger at. When researchers looked at Oklahoma's human-induced earthquake data, fracking's direct contribution turned out to be just 2% of the total. The other 98% traced straight back to the wastewater disposal process, pumping leftover fluid back underground at high pressure. It wasn't the localized blast of fracking that pulled the trigger. It was the sustained, widespread pressure buildup from wastewater injection over a much longer time and a much bigger area. But here's the satisfying twist in the story. Once the science pinned down the cause, regulators and the public actually did something about it.
They permanently sealed off the riskiest injection wells near fault lines with cement and sharply cut back total injection volumes, and the frequency of earthquakes actually started dropping in a very noticeable way. In other words, this was a switch humans flipped on themselves, and one we could flip back off whenever we chose. It was never a disaster we were powerless against in the face of nature. The control was in our hands the whole time.
So now a bigger question comes to mind. If we're pulling out enough material every day to shake the ground like this, could it possibly be throwing off the balance of the entire planet, even its rotation? Let's zoom out from a geological scale to a planetary one. After watching cities sink and massive faults slip, it's only natural to start wondering about the bigger picture. After decades of pulling 100 million barrels a day out from underground, does that really leave the entire planet's physical balance untouched? Could it be subtly throwing off Earth's rotation speed, or even changing the length of a day? Spoiler again, at this scale, the story changes completely. Earth's total mass comes in at around 13 septillion pounds, a number with more than 24 zeros attached, something the human brain honestly can't wrap itself around. Add up every drop of fossil fuel humanity has scraped out of the planet since the Industrial Revolution, and compared to Earth's total mass, it amounts to about as much as flicking a single speck of dust off the surface of a basketball. So the effect of moving that much mass on Earth's rotation is functionally zero. Run the actual numbers, and the physical change in the length of a day comes out to about 0.06 microseconds. That's roughly comparable to how much a single large natural earthquake shifts Earth's rotational axis, an amount so tiny no human being will ever notice it, not once in an entire lifetime. Bottom line, fossil fuel extraction isn't going to knock the entire planet off course. Earth's rotation speed and its orbit stay rock solid, no matter how much we interfere. But this is exactly where a fascinating scale paradox shows up. At a planetary level, there's not so much as a flinch, but at the local level, on the actual ground we live and walk on, in our own neighborhoods, things are visibly collapsing, shaking, and getting contaminated in ways we can't even see. From out in space, it all looks calm and steady, but at eye level, right where we live, a real, ongoing breakdown is happening. And here's the most interesting part of this whole complicated story. Humans didn't just sit back and take it. Remember Wilmington, California, the city that sank nearly 30 feet? Engineers there tried pumping massive volumes of water back into the depleted reservoir under high pressure, right where the oil used to be. Once that missing pore pressure was physically restored, the ground that had been sinking without end simply stopped, almost like flipping a switch. Even more surprising, as pressure came back, some areas actually started rising back toward their original elevation. It's regarded as a remarkable, genuinely successful case of humans using technology to lift a collapsing city back up. That said, this success story doesn't mean we can fully relax. Plenty of unresolved risk is still out there. Estimates suggest that including unofficial counts, there could be as many as 3.9 million abandoned orphan wells scattered across the United States alone. A significant number of those neglected holes are quietly leaking methane into the atmosphere, and measured over a 20-year window, methane is about 80 times more potent as a greenhouse gas than carbon dioxide. To be clear, this isn't some radical crisis that's going to threaten humanity overnight, but the more improperly sealed wells we leave behind, the more that invisible environmental and economic bill, one future generations will end up paying, keeps quietly, steadily piling up. So let's wrap it up. Underground space that's had its oil removed doesn't magically stay as a hollow cave. It collapses under the weight pressing down from above and gets compressed. and the massive volumes of wastewater pumped back underground to fill that gap are literally shaking the ground beneath our feet. The planet as a whole may look perfectly fine, but the surface environment we actually live on is going through changes that can't be undone. But the most important takeaway from this entire story is that the power to stop and control these human-caused changes is also in our hands. Honestly, when I first started researching this topic, the first image that popped into my head was that same giant hollow cave deep underground. But the more I cross-checked the sources, the clearer it became that the cave was never real to begin with. The actual science behind this is far more intricate than any of us would have guessed. The conclusion that stuck with me most while digging into this topic is that this was never some unstoppable tragedy humanity just has to helplessly endure. Wilmington, California gives us a real precedent. Humans refilled that pressure and stopped ground that had been endlessly sinking. And that tells us something important. The marks our civilization has left on the Earth can, ironically, be healed and restored through even more advanced technology and better systems. The possibility that we can use intelligence to clean up the side effects our own industrial technology created, that's exactly the part I want to hold more hope for. I tried to break down this complex, sometimes intimidating energy and geology topic as objectively and clearly as I could. I hope you walked away with something useful. This has been Olivia, host of Professor Her Room, where we explore the intersection of global geopolitics, history, and culture. Thanks so much for watching.